Today I'd like to go back over direct variation. We spent some time talking about this model of direct variation, y is equal to kx, where k is a constant of variation. These first few problems are set up for us already in the proper form. K is equal to -4 in the first one. We realized in our last class that the model of direct variation starts graphing at the origin, and then from there we can graph. Starting at the origin, k is also our slope. Slope is a ratio of rise over run. If it's a whole number, it's over 1. Count down 1, 2, 3, 4, and over 1. And we have our graph. Second one, again, finding the value of k. K is equal to 6, which is also my slope m. So I'll start at my origin, and this time it's a positive number. I'll count up 6 and over 1, and there's my graph again. Last one on this type, if I have y is equal to kx, my k here is 5 over 2. Start graphing at the origin. My slope is a ratio of rise over run. It tells me it's positive. Count up 5. 1, 2, 3, 4, 5, and over 1, 2. And there's your graph. Now what if I asked you to find the constant? All right, and again, we had statements yesterday's lesson saying x and y vary directly. And they'll give us the conditions when x equals 5, and maybe y equals a -15. Find k. To find the constant of variation, y is equal to kx, y is -15, and x is 5. Divide both sides by 5, and k is equal to -3. Now that I have my constant, just write it in the equation. Y is equal to -3x, where the constant of variation was -3. A quick graph of this model of direct variation starts, as all of these do, at the origin. We'll count down 1, 2, 3, and over 1. And there's my point. There's my line. The last thing they asked us to do was to evaluate. Using this model, y is equal to -3x, they might say, find the value of y when x is equal to 7. Substitute 7 in for x and simplify. Y is equal to -21. We input x value of 7. We output a y value of -21. And that's our model of direct variation. Today, I wanted to take a little look at arithmetic sequences. A sequence is a set of numbers, and each of those numbers in the sequence is called a term. And they're in a specific order or a pattern. So now we're looking at these numerical patterns that increase or decrease. If they increase or decrease at a constant rate, it's called a common difference, and we'll refer to that as D, the common difference. We'll look at each set and determine if it is an arithmetic sequence, and if it is, we'll state that common difference. You have to find the change. You're going to subtract the two numbers. We notice that they're going up, and I've noticed that everything is plus 2, plus 2, plus 2. We can extend the sequence, plus 2 and plus 2, so the common difference, D, is 2. This is an arithmetic sequence because there is a common rate of change. So we're determining if it's the same going from term to term, it's an arithmetic sequence. It could be rising or falling. It could be increasing or decreasing. I go from 33 to 29, 29 to 25, 25 to 21, 21 to 17. Looks like if I find the difference between the two, we are subtracting 4 repeatedly. Let's subtract 4, and we'll subtract 4 again, and my common difference. All right. Next one. Now again, looking for a pattern, it doesn't always have to be adding, because if it's not a constant, we might have to sometimes multiply or look for another kind of pattern. 1 to 4, 4 to 9, 9 to 16. This is not arithmetic. If I'm noticing, it's the square. 1 squared, 2 squared, 3 squared, 4 squared, 16, 5 squared, 7 squared, oops, sorry, 7 squared is 49, and 8 squared, wait, so it's not an arithmetic, there's no common difference there. 3 to 6, 6 to 12, 12 to 24, 24 to 48. See if you can find a common difference, or if not, just complete the pattern in the next two numbers. Now we'll be doing more with these besides that, finding the common difference and then continuing the pattern, and I'll save these others for our session in class today.